This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2019 AP Calculus exam free response question AB3 BC3. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. I'll present the solution to each problem in a little greater detail than given in the scoring guidelines. And even though this question was not calculator active, I'll show you how to use technology to explore and answer parts of this question and to confirm solutions, where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions. Some of these will be associated with the information given in the problem, and some may be calculator active. This problem involved the graph of a continuous function f, defined on the closed interval -6 to 5. Part of the graph of f, given in the figure, consists of two line segments and a quarter circle centered at the point 5, 3. In addition to the points marked on the graph of f, the point 3 minus the square root of 5, is also on the graph of f. In Part A, we're given the value of a definite integral and asked to find the value of a related definite integral. Note that the student is reminded to show the work that leads to the answer. And in Part B, we're asked to evaluate a definite integral involving the derivative of the function f. In Part C, we're given a new function g, defined in terms of a definite integral, and we need to find the absolute maximum value of this function over the interval -2 to 5. And finally, in Part D, we need to evaluate a limit. Part A was worth 3 points. The most common method for solving this problem was to use an appropriate property of integrals. So 1 point for using a suitable property of integrals to write an expression involving the desired definite integral. 1 point for evaluating the integral from -2 to 5 of f of x dx, and 1 point for the final answer. Part B was worth 2 points. And here, students had to apply the fundamental theorem of calculus and some basic rules about anti-differentiation in order to solve this problem. So 1 point was awarded for using the FTC associated with the definite integral of f prime of x. This involved finding the antiderivative of f prime of x and symbolically subtracting f of 5 minus f of 3, and 1 point for the final answer. Note that there are two very similar solutions to Part B presented in the scoring guidelines. The first solution presents two separate definite integrals without the symbolic antiderivatives, and the second solution presents the antiderivatives and then the evaluations. These were the two most common solution methods presented by students. Part C was worth 3 points. One common method for solving Part C involves the candidates test, or a table of values. The first point was a conceptual point, awarded for the first step in searching for candidates, for stating that g prime of x equals f of x. The student did not have to set this expression equal to 0 to earn this point. The second point was awarded for identifying x equal -1 as a candidate for the location of an absolute extreme value. Now, this is a rare instance in which the student did not need to show the work that produced this candidate. And the third point was for the answer with justification. Here, the answer is the absolute maximum value, not a point, and not just an x value. And the justification in the scoring guidelines is the table of correct values. part D was worth 1 point, simply for the answer. This limit can be found by direct substitution. And remember that a final numerical answer does not need to be simplified, but if it is, then it must be correct. And the arctan of 1 does not need to be evaluated here. It's a numerical value. Let's take a closer look at these solutions. And even though this was not a calculator active question, let's consider the use of technology to visualize and solve some of these problems. To solve part A, rewrite the definite integral from -5 to 6 of f of x dx using a property of integrals. Now remember, using this property we can actually split this integral into two pieces using any value of c. But the property is easier to visualize on a graph, if c is between -6 and 5 in this case. We're given in the problem that the definite integral from -6 to 5 of f of x dx is equal to 7. And we can find the definite integral from -2 to 5 of f of x dx by associating the definite integral with area. Now remember that in order to find the area under the curve from x equal 2 to x equal 5, we need to find the area of a square and then subtract a quarter of the area of a circle. That's where the 9 minus 9 pi over 4 comes from. And then finally, we can solve for the desired integral. Here's an example of how we might use technology to solve this problem. On the TI-Nspire, first define the function f piecewise. Now, in order to do this, we need to find the equations of two lines and the equation for the quarter circle. Now, just to confirm my definition of f, here's a graph of the function. And this graph agrees with the one given in the free response question, thank goodness. Using the appropriate property of integrals, I can simply enter an expression to solve for the desired integral. Notice that I get an exact symbolic answer, and that's pretty cool. You might also try to find the definite integral from -2 to 5 of f of x dx on the graph screen, just for contrast and comparison. Here's an example related to the free response question. The continuous function f, similar to the one given in the FRQ, is defined on the closed interval from -2 to 8. The graph of f is given in the figure and consists of two line segments and a half circle centered at 5, 0. The function g is defined similarly as the definite integral from -2 to x of f of t dt. In part A, find g of x for these values of x. In part B, use these values to sketch a rough graph of g. In part C, explain the relationship between the graph of g and the graph of f. And finally, in part D, find an analytic expression for the function g, and compare the graph of this function with the graph produced in part B. In order to solve part B, we need to apply the fundamental theorem of calculus, a basic anti-differentiation formula, and a few properties of integrals. The integral of f prime of x is f of x. The integral of 4 is 4x. And constants pass freely through integral symbols. We evaluate the antiderivative at the upper bound and the lower bound. Note that f of 5 is read from the graph, and f of 3 is given. Subtract, and simplify if desired. Here's a technology solution. And remember, I already defined the function f. Now, it's a little taxing to write the derivative this way, but again, this returns the exact symbolic answer. And I didn't specify the value of f of 3 in any way. I'll solve part C using the method shown in the scoring guidelines by using a table of values. First, take the derivative of the function g using the fundamental theorem of calculus. Set this expression equal to 0. By examining the graph of f, there are 3 values for which f of x equals 0. Note that x equals 5 is an endpoint of the interval, so this will be included in my table of values anyway. And just to be complete, there are no values where the first derivative of g does not exist. Here is a table of values for g, with x values, where g prime of x is equal to 0, and the endpoints of the interval. I need to evaluate g at each value of x by associating the definite integral with area. Then we simply select the largest value in the table, here 11 minus 9 pi divided by 4. Now you might have to make sure that this value is greater than 1/2, but it is, and that's the absolute maximum value of the function over the interval. Here is a technology solution. First, I defined the function g, and then I found the values where g prime of x equals f of x equals 0. On a lists and spreadsheet page, I evaluated g at each candidate. And just to make it easier to select the absolute maximum, I included a column of decimal approximations. The absolute maximum value is 11 minus 9 pi divided by 4. In Part D, we can solve this limit by direct substitution. So substituting x equals 1 into the quotient yields this expression. To find f prime of 1, we need to find the slope of the line segment that is part of the graph between x equals 0 and x equals 2. We can read f of 1 from the graph, and arctan of 1 is a common value. Now, the student doesn't need to simplify a final numerical answer. So this expression is acceptable on the AP Calculus exam as the answer. But remember, if the student chooses to simplify, then it must be correct. And here's another example. Try to evaluate this limit. And one comment here, you can't use direct substitution in this problem. Here's another example. The solutions depend upon the properties of integrals and associating a definite integral with area. The figure shows the graph of a function f, and there are 5 labeled values on the x-axis, and the graph of f passes through the origin. The areas of the regions between the graph of f and the x-axis are labeled. Determine the value of each definite integral. And finally, here's one more problem extension. Let's consider the portion of the graph of f as given in the statement of the free response question. The function g is given by g of x is equal to x squared minus the definite integral from minus 2 to x of 3 f of t dt. Find the intervals on which the graph of g is increasing, and find the intervals on which the graph of g is decreasing. Find the intervals on which the graph of g is concave up and concave down, and find the inflection points on the graph of g. Find the absolute minimum value of g on the interval minus 2 to 5, and justify your answer. And finally, carefully sketch a graph of the function g over the interval minus 2 to 5. And you might consider using technology to solve this problem. I hope this video gives you a better idea of how to solve this free response question, and some good ideas for additional practice AP Calculus exam type questions, how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. This free response question presents some good opportunities to discuss and really understand some properties of integrals and the candidates test to find absolute extreme values. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.